So let me introduce Ivan. Ivan is a senior researcher at INRIA Paris and head of scientific board at Vision Labs. He has served as program chair for CVPR'18 and is a regular area chair for CVPR, ICCV, and ECCV. Notably, he has many famous work around action recognition and video understanding. And just note to new folks recently joined, the talk will be 25 minutes plus 5 minutes QA at the end of the talk. If you have any questions, please send in the chat channel and I will raise them during the QA part. Ivan, are you online?
Yes, I'm online. Can you hear me?
Yeah, we can hear you. Great. Yeah, I think you can take over.
Okay. Thanks a lot, Mike, for introduction and for inviting me to this workshop. So I'll try to share my screen now. So I think you should see my full screen slides. Is it correct?
Yes, it looks great.
Okay, perfect. Yeah. Okay, so I tried to match the topic of my talk to the topic of the workshop. So I'm going to talk about long-term, but trying to get it towards affordable long-term video understanding. And this is work done with quite a few colleagues from INRIA, from Prague, from DeepMind, and from Facebook Paris. So I'll try to pack 3 papers in this talk. And so I'll start with a work which is probably most related from our side to this workshop, is a long-term spatio-temporal modeling for action detection, which was done with, mostly by Makarand and Vijay in our lab. And so then I'll talk more about how to make the long-term video understanding more affordable, because it's not only that we have some issues of understanding and modeling the long-term relations in the video. It's also also a practical problem, because if you want to learn a model for 1 hour instead of for just a few seconds, so there is a memory problem, there is a speed issues, and so I'll talk a bit about this. So in one work which is was presented earlier this CVPR about text to image or text to video retrieval. So there will be some video in this work, and the last part is going to be actually it's not going to be any video there, but so it's a new method which just came out on Archive, and so it's about transformers as well, and how to make transformers efficient with respect to the number of token inputs. And again, so although this work is not about video, I think it can be easily extended to video, and it may show some benefits. Right. So let me start with the first work, and so again, it's done by Vijay Kumar and Makarand Tapasvi, who are both postdocs in the lab last year. So what's the goal? The goal is to detect atomic actions, so nothing new, so some actions which appear in a short period of time, and to do it in a long videos such as movies, for example. So what we all know, or if you don't know, it's intuitive, is to assume that there are correlations, or you can call it correlations or context. So the actions depend on each other spatially. So within frames, for example, if someone is taking something from one person, then most likely you also see that someone else is giving the object to the person. So that's this is just physics. Of course, not always happens. You may not always see it. So and then if one person is swimming, quite likely there is somebody else is swimming nearby. Right. So the opposite, like if there is someone is swimming, then next to the person is probably not nobody is riding bike. So these correlations happens in space. There are also correlations which happen in time. For example, if so first, before entering, usually something, window or door is opened, or if someone plays musical instrument and singing, this can take turns. Or working on computer, if the person is working on computer, it's likely that the person is going to continue working on computer. So we want to capture these correlations, and not just to capture it for the sake of predicting or capturing, but to help us to recognize actions. So we want a model which describes this correlation, takes advantage of them, learns them, and takes advantage of these correlations in the inference process. And again, so the evaluation will be on detecting particular instances of actions. So the questions to ask are what other people are in the key frame are doing, what is the same person is doing over time. So these are the questions which we want our model to help us doing. And of course, these questions we want to infer the answers jointly for over space and time. Okay, so just very short about the model. The model is not pretty standard. So we have a 3D scenario person detector, which tracks the people. We have a 3D scenario on top of them. And then to model relations between actions, we have a graph neural network where the nodes are short snippets of person action. So each node in this graph corresponds to the box tracked over a short period of time. And the ages could be temporal and spatial. And then during learning, so we want to learn graph neural network. And in the inference process, we iterate over it and to receive the answers. So what is spatial context? Yeah, so from the correlation matrix, so if someone, for example, is shaking hand, then in the same scene, there is likely to be someone else to be shaking hands. And we want to model these interactions, and we do it by edges between the nodes of the graph. And similarly for time, so we have, for the same person, we have edges which bridge over time to model if the person is doing now something, what is the person going to do next, right? So important thing is, so it's not a complete graph. It could go for a complete graph. It would be just more complicated. So here we have in each frame a complete graph over space, and then in time it's a complete graph over time, but just for one person. Okay, but because we do iterations during inference in the GNN model, so the information gets propagated even over time between different people, right? So how we evaluate these models? So we look at our dataset, which contains many actions and multiple people, and annotation about every second. So there are some challenges because there's a quite bias to some actions. So the ratio between actions can be 1 to 1,000, and the average precision is the metric. So here are some results. So MLP is the baseline where the action would be detected just independently. So for each subtract, you would just classify if the action happens or not. And now, so what previous work has done, so they've been doing GNNs just in space. And so what we see here in the last 2 lines, that adding temporal, just doing temporal context with GNNs, it's already outperforms the baseline, and the spatio-temporal brings even more improvement. So here a bit more ablation studies with respect to MLP. So you see that temporal brings most, then spatio-temporal brings even more, and spatio-temporal over spatial brings about 1% as well. All right, so here just a few quality results about which shows. So if you look at the numbers here, so numbers correspond to the rank of a particular example. So here, example handshake. So with the MLP model, this example would be ranked as 66, and with our best model, it gets higher. So it gets high confidence, and so the rank is lower. So this is for person-person interactions and for person-object interactions. So what basically this work shows that GNNs, and there are some details, of course, in the paper which I didn't describe. So you can construct GNN which look at the spatial context and temporal context, learns it, and brings improvement when you try to do inference and trying to look at all actions in one shot of a movie versus just if you look at each video, each short clip independently. Okay, so yeah, not huge progress, so numbers are quite low, but still, but it shows that temporal dimension does have signal. All right, now I want to switch a bit and talk about another problem, which is text-based image or visual search. So where you put a query in terms of a text and you want to find the corresponding image or a video. So the technique is applied in this paper. So this is a CVPR paper which was presented this week. The technique can be applied both to image retrieval and video retrieval. Right, so what's the problem here we want to consider? The problem is the efficiency. So we have typically, when you do say image-to-image search or text-to-image search, you usually have full efficiency reasons. You have encoder for each, for your query and for your data set. And then it's great if you can have, if you can represent an image or a text as a feature vector, which by doing a dot product will produce you the similarity score. Why is it good? Because this can be very fast. Dot product, computing dot product for billions of vectors is very fast, can be done with approximately nearest neighbor search and so on. But of course, one can imagine that this is not a very expressive model because you encode two modalities separately. What is more expressive, and we show in the paper, is that if you do encode the image and text or video and text together, for example, with a transformer. So transformer is a state-of-the-art architectures now. So if you represent an image, you have some initial representation of an image, some initial representation of a text, you do cross attention or self-attention on these representations, and then produce the similarity score. This actually works much better. So here you can see numbers. So if you do dual encoder, so two ways separately versus vision-text transformer, which does it jointly. So the vision-text transformer works better, but is much slower because why is it slower? Because you, for each pair of text and image, actually have to run the network. It's not just dot product as on the left. You have to run the network, and this will be like running this for billions of even the millions of images or videos real time. This is impossible. So that's what I already basically said. So what's interesting is, can we get the best of the two worlds? Basically, try to get the strength of joint encoders for vision and text, and get the speed of dual encoders. So that's the main subject of the paper. So we have a fast model, which is a standard model, which encodes, say, images or videos with CNN architectures, and a standard representation for text, and then we learn on top of it, we learn layers which learn the joint embeddings. And then we also have a slow model, which is first process images or videos with a CNN, and then it has a transformer decoder which enables richer cross-attention representation. Right, so these are two models. Now, how to combine them? So the combinations goes in two ways. So first you try to learn the fast model by distilling knowledge from the slow model. Right? So distillation, noise distillation, of course, been explored a lot in vision domains in neural networks. So here is a bit particular because we are distilling from a transformer, which is a joint encoder, into a dual encoder. So it's not straightforward because the losses are different. So in order to do this, so we propose a new distillation procedure, which works as follows. So if you have a batch, you can compute the you can compute similarity of a text and visual modality within a batch and to produce a distribution of it. And you can do it both with a dual encoder and visual text transformer. And then, so our distillation loss tells that these two distributions should be similar. And this actually works. So we show that you can train you can train a dual encoder which works better if we distill the knowledge from the encoder. And then there's also re-ranking, which I will mention in a second. So, okay, re-ranking works. So if we first run the slow model and get top, say 100, top K matches, we can, in a very fast way, we can still apply the slow model at the very end just to get the even better results. And so how the results look like. So here's an example on Coco, on still images. So if you just use the fast model, say so it works like gets record 5 about 54, 53. And so you see here that the slow model gets much better right here. So the distilled model, so it works as fast as the fast model because we distilled the fast model from the slow, but you see that it gets much better performance. And then the re-ranking gets us additional quite a bit of percents. And so we are basically by spending, well, the re-rank model is by constant factor slower than the fast model, but this you can control. And you see that you almost don't lose any performance, but we get 100%, sorry, 100 times the reduction then. And here, so we get also stated results on Vatex video retrieval dataset. All right, and so I'll jump to my third topic, which is also about transformers. So transformer architectures nowadays they are outperforming CNNs. It would be great, and of course there are work which are using transformers nowadays for vision, for images, and for videos. So, for example, Clipboard, which was presented with CVPR and VIT, which is one of the first papers which does the full transformer architecture for images. So, what's the problem? And especially for video, so if you want to analyze if you want to do long-term video understanding, it's already hard with CNNs, which are linear in the number of inputs. So problem with transformers is that transformers are even worse. They are quadratic in the number of inputs, where inputs are terminology of transformers called tokens. Tokens could be patches of an image or one frame, for example. So if you or patches of one frame. So for example, if you're talking is one frame and your video is 1,000 frames long, for example, then your memory complexity will be on square, which is obviously doesn't scale very well. So this is a problem. Few works recently addressed this by approximating, trying to come up with some approximations of the transformer. So first, let's see why is it actually in square. So here's a self-attention from our original paper from Cross-Covariance et al. So we see that x, if x is the data, n times d is the feature dimension, n is the number of tokens, for example, image patches or video frames. So we have keys and queries, or keys and queries are projections of x to some matrices which are with weights which are learned. Okay, and then so the self-attention is a matrix. Basically, it's a dynamic weights, data-dependent weights, which then gets multiplied to the data again, and this matrix is normally it's a n squared, because that's how it is. So what this work is about is, so we are proposing a transposed self-attention, and in mathematical terms this is very easy actually. So what basically if you so if you see my mouse, so all what happens is that you take this matrix multiplication and you transpose it. Okay, but what's advanced, so here's the difference. So it's the same matrices, same keys and queries, just attention is just transposed. And what happens now is that your attention matrix is not anymore of size n by n, and n is again it's the say length of the video, for example. So it's variable, n can be very large, but in the cross attention, the size of self-attention matrix is now dk by dq. Basically, it's a feature dimension of a feature square. It's fixed, so it's constant. So this is the advantage. It can be also modified. Of course, d is the parameter which you choose, and you cannot. Well, you can choose, but it's given by the data. If your video is long, it's long. So d you can reduce, and it's usually smaller than n. So why does it make sense to do transpose? So basically, first, what is this? So standard self-attention is done on the tokens. So here you can see that the attention is done on the feature dimensions instead. Why does it make sense? So I can think of so what are the ingredients inside the standard self-attention? So we can think of it as a gram matrix X transpose. And what is key ingredient in our attention, cross-covariance attention, is the actually covariance matrix, because if you just transpose G, well, if you transpose xt, so you get xt(x), and this is a covariance matrix. What's interesting is that the non-zero part of eigenspectra of G and C are equivalent, and this gives intuition why it may make sense to substitute G by C. And now let's see what happens. Okay, so once we substitute and we transpose our attention, so we put it as just a block in excite layer, which also contains local patch interaction and feed-forward network. But the main thing here is that the self-attention here is not dependent on the number of tokens anymore. And that's what we see on this plot, which is a memory usage of excite self-attention. So if we use patches, say 16 by 16 or 8 by 8, so it takes more memory, of course, if you do 8 by 8 patches, because there are more of them. But we see straight lines as expected, so they are linear, the memory usage is linear in the image resolution. While if you take standard image transformers, so they are quadratic in the number of tokens, and that's the problem. Also, what to see here is that for ImageNet classification, now on y-axis is a top 1 accuracy. We see that, for example, 16, if you take 16 by 16 patches or 8 by 8 patches, it clearly brings improvement. And that's just ImageNet. So for other tasks like image segmentation, for example, it's known that going to high resolution is important. And that's what our architecture enables us to do, is to go for more patches, high resolution, potentially in video for long frames, for long temporal extents. Some quality results, so that's a big image of 6,000 by 4,000. So we can easily run the segmentation and detection on this image because we are linear in the number of tokens. And here's a visualization of self-attention. So you take a class token, you do dot product with the spatial tokens, and it produces the frame by frame, it produces such attention maps, which clearly show that it focuses on interesting things in the scene. Just some more intuition why this is actually working. So more results are in the paper, and actually not just for image classification, but for object detection, segmentation, and image retrieval as well. All right, I think I'm out of time, and so here's just a quick summary of what I've talked about. Thank you for listening.
Yes, thank you, Ivan. Let me see if there's any question from the audience. Actually, I have one question regarding the second work of text visual retrieval. So, like previously, I worked at Facebook AI, and I think in many these like big companies for social media, they have very complicated ads ranking model. So, if I understand it correctly, you only have one pass of re-ranking, right? Or you plan like for this kind of like ads model, in practice, they usually have multiple stages of ranking, like rank from 10K candidates to 1K and 100, and finally get the top ones. Do you consider maybe it's a promising direction in the future? We design this kind of multiple ranking system.
So you mean to optimize even more this? So here we just had 2 models, but I imagine if you have multiple models, like one super slow, one super fast, right? So you could do this, the stages. Yes, you could have several. Yes, you could have several stages of re-ranking. Sure, that would be possible.
Cool. And also for your first work on the graph construction, I think it's also very important for this long form knowledge and video representation. So just one quick clarification question about, I think if I understand correctly, you have basically person detection at individual frame, and then try to use this graph network to link even the same person, but from different frames. So it looks like there's no tracking module has been used here. Do you think maybe it's kind of like essential to use tracking, an individual tracking module here to link the same person over time?
Sorry, maybe checking module, what do you mean by checking module?
Like a person checking, basically it can automatically associate the bounding box of the same person from different frame into kind of like checklist for a specific person.
Right, so there is obviously tracking, right? So there is just individual names. So we have a tracking, which so we know which person, like if in
Oh, I see.
frames, we know which person corresponds to 100 frames before.
Got it. Makes sense. Cool. Thank you, Evan. Very helpful information, and I think it will trigger a lot of follow-up works.
Okay. Thank you.